Hey, everybody. Thank you for joining. I'm super excited to talk to you today about TensorRT LLM 1.0. TensorRT LLM 1.0 is a product that we just launched. It's been in the making for over 4 years now. We've developed this in collaboration with some of our closest partners, taking feedback from our early adopters and with close engagement with the open source community. So we're super excited to have reached this point today, and I'm looking forward to getting to share with you more about 1.0 today. My name is Lake. I'm a product manager at NVIDIA. I manage LLM inference software products. I'm joined by my colleague, Max, who will be helping moderate the session, facilitate some questions today. I'd like to start by talking to you a little bit about what is TensorRT LLM. So we built TensorRT LLM with the goal of pushing the frontier of inference performance for large-scale LLM deployments on the NVIDIA platform. We do this in 3 key ways. So the first is for deployers of applications who want to put out the most popular open source models. TensorRT LLM enables you to have end-to-end deployments with optimized performance for models like GPT-OSS, DeepSeek, Llama, QN3, and more. The second is that we package this deployment capability into an extensible Pythonic framework that enables developers with custom or proprietary models to leverage the technology for their own custom deployments. And lastly, we use TensorRT LLM as a conduit or a delivery vehicle of new technology and new innovation in the inference space to bring it out into the LLM inference ecosystem and lift all of our ecosystem partners. TensorRT LLM 1.0 is a new version of the product that was just launched with a core focus on usability. Now, usability means something different to different people. For deployers, we want to make the experience extremely seamless to take the most popular model from research into production very quickly. For framework developers, we wanted to build a modular system that allows you to take components and leverage them for your own customized software. And we also wanted to make this easy to use for people with custom models, being able to research the system and extend it with new techniques and new features. So the 3 key components and key ways that we achieve these goals. So the first is that with model authorship, we've re-architected the system to enable you to author new models in PyTorch. This means if you have existing Torch modeling code, say from Hugging Face, you can transport that into TensorRT LLM, tweak a couple things to register it with the system, and get started from there. At that point, optimization becomes an iterative process. So you can swap out, say, a vanilla attention layer with our custom attention Torch custom op, or you might register different components like our gems for advanced parallelization techniques. And you can do this in a step-by-step manner. The other thing this enables you to do is leverage standard Python and PyTorch debugging techniques and tools developed in the developer ecosystem for PyTorch. So if you want to print out the intermediate value of a tensor or leverage PDB for debugging, you can do so now with TensorRT LLM as well. The new runtime is designed with modular Python building blocks. These define clear Python interfaces for core runtime components and provide Pythonic implementations underneath for maximal hackability. So if you want to extend the system with a new feature or curate behavior based on your needs, you can either modify our Pythonic implementation or adhere to a top-level Python protocol and bring your own system blocks. Lastly, without the need for ahead-of-time compilation or explicit engine building, you can quickly iterate and change build parameters or move between hardware with using the same software. Lastly, all of this is open sourced and developed on GitHub, so you can engage with our development team and help drive the roadmap directly on GitHub. When we think about the value of TensorRT LLM, we look at how can we push the boundary of inference performance. So we do this across looking at optimization opportunities across the stack and co-optimize our software and hardware together. So when moving from Hopper generation to Blackwell generation, we leverage new techniques like FP4 tensor cores, the large NVLink domain for disaggregated serving, and wide expert parallelism for sparse MOE type models. This kind of co-optimization and laser focus in just optimizing for the NVIDIA platform enabled us to deliver an astounding 8x boost from Hopper to Blackwell generations. But we continually optimize and look to push the boundary of performance. So in the next month, we look to push performance by an additional 4x for the DeepSeek R1 model. When we're looking at this chart and defining the performance frontier, we look at really two key axes. So on the x-axis, you'll see the interactivity or user experience. This is how fast tokens are flying across your end user screen. And then we look at the production capacity of your total system. How many tokens can your system output at any given time? And we look to stretch out the tail of this to improve the user experience and push up the curves to improve the production capacity of your system. And by pushing this Pareto frontier out with co-optimization of hardware and software, we're able to push the boundaries of what's possible for LLM inference performance. TensorRT LLM has three key categories of features that enable us to deliver this ease of deployment, ease of extensibility, and driving the performance boundary forward. The first category of features in TensorRT LLM include optimized and tunable kernels for the most common LLM inference operations. So these include fast attention kernels, gem kernels, communication kernels, and so on. These are modularized and implemented as Torch custom ops that are then executed in the forward pass of your model. But just optimizing the forward pass of your model isn't often sufficient for getting the end-to-end performance that you need for your large-scale deployments. And for that, we provide an efficient runtime to actually deploy these LLMs in. This includes techniques like in-flight batching, advanced KV cache reuse, speculative decoding, advanced parallelization, and so on, that drive the end-to-end system performance beyond just the individual forward pass of your model. And lastly, we package all this technology up into a Pythonic framework that allows you to author models in PyTorch and customize your system behavior with Python runtime blocks. To get started with TensorRT LLM, there are really three key ways that you can interface with the system. The first is that you can launch a server in one line of code using the TRTLM serve CLI. This is a server utility distributed in the library and enables you to deploy a single instance with an OpenAI compatible endpoint of your model. For larger scale deployments and orchestration of a multi-instance deployment, you can use a utility like Dynamo that provides advanced data center scale optimizations to further boost the performance, the end-to-end performance of your system. And lastly, for the most flexible and stable API, we recommend using the LLM API. This is stable across 1.x versions, so you can rely on this for stability and seamless deployment, but this is fully featured for all types of customization. The system is architected in a few different layers. So in the first layer, we have the serving layer. So this would include TRTLM serve, Dynamo, or the ability to bring your own serving layer. Typically, these are built on top of that stable LLM API that's simple and fully featured. And for advanced users who want to get into the system, we offer the PyExecutor. This is an internal API that's rapidly developing, but represents sort of the internals of the system. The PyExecutor wraps our engine and our runtime. So the engine encapsulates these optimized kernels and select graph utilities to combine it into an abstract concept of an engine. And that engine is then deployed into the runtime with components like the batch manager, KV cache manager, and workflow extensions. Lastly, I'll note that TensorRT LLM is developed fully in open source. It's developed on GitHub, and so the latest changes are always visible. You can see individual commits for easy merging and easy debugging. We offer a public CI/CD that enables you to test and test your contributions and merge in PRs. On GitHub, we also provide tech blogs that detail how we architect new innovations and new techniques. This enables us to lift the performance of our ecosystem partners with this technology. So there are really two key techniques that we use to lift the performance of ecosystem partners. The first is open source development and tech blogs on GitHub, but we also leverage a library called Flash Infer. This enables us to push out kernels from TensorRT LLM into this library and easily integrate that into our ecosystem framework partners. Flash Infer is a great open source project that enables any kernel developer in the ecosystem to customize, modify, and contribute back advanced kernels for LLM inference. In fact, many kernels are often re-ingested back into TensorRT LLM from Flash Infer. So through these two key channels, we're able to not only push the frontier of inference performance forward on the NVIDIA platform, but distribute that technology and innovation out into the inference ecosystem to rise performance for everyone. I'll take a minute here to pause for questions before going to a technical deep dive for how to use the new architecture. Great. Let's keep going. So I'll transition now into a technical deep dive into how to use the new architecture. So first of all, I'll show you how to deploy a GPT-OSS 120 billion parameter model using TensorRT LLM 1.0. So you can use the TensorRT Serve CLI to launch an OpenAI compatible endpoint, compatible with the chat completions endpoint using TensorRT Serve. You'll want to configure the server to make sure you're getting the best performance. And you can do so with a config.yaml file. This enables you to configure key components of the system, including KV caching, speculative decoding, select kernels, and more. You can train your own Eagle heads, or we publish pre-trained heads on Hugging Face for you available to download. This is an example of how to deploy a specific scenario for GPT-OSS. But for more examples, for more models and different scenarios, you can check it out on our deployment guides on our documentation page linked below. TensorRT LLM 1.0 is designed with modularity in mind. So on the right, you can see a pseudocode of what the system is running when it processes a request coming in. The first thing it'll do is schedule requests into the system, call this batch management. It'll do an allocation of KV cache and make sure that you're enabling effective reuse of your cache. Then you'll execute the forward pass of the model. And lastly, you'll do some decoding and sampling logic. Each of these box components represents a modular component of the runtime that can be customized and tweaked based on your requirements. This highlighted pass, the forward pass of the model, is implemented in native PyTorch. And so you can start with any Torch implementation, modify a few key components to register with the system, and get excellent performance out of the box. In order to customize one of these runtime systems, you might be able to implement, say, a new model directly with PyTorch. So if you take existing Torch modeling code, say from Hugging Face, you can pull that into the system, register a few key components, and they get running. The first step to do so will be defining your model configuration. This might be the config.json directly from Hugging Face, or you can author your own for a custom model architecture. The next thing you want to do is implement your submodules. So you want to replace the key components of your model architecture with Torch custom ops that are backed by our optimized kernels. So you might want to say replace your vanilla attention with the TensorRT LLM implementation of attention for better performance and registration with our KV caching system. Lastly, you want to load the weights into the model to actually load the checkpoint into the TensorRT LLM system. And then you can even just register the model locally with your deployment without having to manage any upstream changes. If you want to modify the runtime, say by implementing a new scheduling strategy, you can do so in a modular way. We offer a capacity scheduler class that you can subclass and override any relevant methods with your own implementation, all in Python. Once you've written your own implementations of the schedule request method or any other relevant methods, you can register your capacity scheduler with our system and start running from there. Great. That concludes the technical deep dive. I see a few questions here in the chat. There's a question about how does TensorRT LLM 1.0 support different model architectures for different models. So we have support for a variety of different architectures, including both LLMs and VLMs. These include hybrid models, vanilla transformers, decoder-only models, SSMs, and so on. So we have examples of all of these kinds of models already supported, and authoring support for new models involves taking existing Torch modeling code and moving it into the system. Great. Another question of how to optimize large language models with TensorRT LLM 1.0. So there are a few key components for optimization. There's registering different kernels, so replacing your attention or your gems with TensorRT LLM kernels. The other is leveraging the runtime components of the system. These components, including speculation or parallelization, can drive huge benefits both for interactivity and production capacity with sort of X-factor gains that really are important for end-to-end performance beyond just the forward pass of the model. Great question. What hardware platforms are compatible with TensorRT LLM 1.0? So TensorRT LLM focuses on optimizing large-scale LLM deployments, particularly in data center scenarios. So we're really focused right now on our Blackwell generation of GPUs. We're looking at our Rubin architecture that's going to be available next year. But we also extend support back into older generations of GPUs, including Hopper, Ampere, Ada, and so on. Our ultimate goal is for the most important workloads, how can we drive the performance boundary forward? And so we're often looking at the latest and greatest in techniques and hardware, software co-optimization to push the frontier of performance forward. How do I deploy TensorRT LLM optimized models in production environments? It's a great question. So there are a few different ways to do so, and you can really tailor this based on your requirements. If you want to build your own server and build your own load balancing, you might want to interact with a lower level API like the LLM API. If you want prepackaged data center scale optimizations, you might want to interact with something higher level like Dynamo that orchestrates multiple instances of your model, provides disaggregation support, does smart routing between instances, and a whole lot more. What tools are available for debugging and profiling models in TensorRT? So because TensorRT LLM is architected in PyTorch and Python, you can leverage all of your existing developer tooling around the Torch and Python ecosystem. This includes PDB, this includes printing out intermediate tensors, but you also may want to use more advanced tools to profile your model. So this is where things like Insight systems can come in to identify bottlenecks and bubbles in performance and find out ways to squeeze out every drop of perf available. How do I handle dynamic input shapes for TensorRT LLM? That's a great question. So one of the most common places where you'll see dynamism in your input shapes will be in your batch dimension. So TensorRT LLM can naturally handle dynamism in, say, your input sequence length or your output sequence length natively. But when you're batching at different concurrencies, you'll need to leverage CUDA graphs to make sure that you can mask some of the overhead of the host that's introduced to keep your GPUs efficiently driven. This requires a bit of a startup cost that you pay ahead of time when you're instantiating a new model or starting up a new instance. You'll capture CUDA graphs for a few different graph sizes or batch sizes and currencies. And then at deployment, you can either capture it for all deployable sizes or pad to the nearest size. So you pay a very marginal runtime cost and end up getting a huge benefit for masking overhead from your CPU. It's a great question. It's a great question. What's the migration effort from the previous TensorRT engine-based TensorRT LLM to the new TensorRT LLM 1.0 architecture? So for early adopters who are using the TensorRT engine-based architecture, they would have noticed that you'd have to compile these engines ahead of time. So if you're already deploying with the LLM API, that engine compilation step was abstracted from you from a code level, but you would end up with these engine artifacts that were hardware specific and config specific that you'd have to rebuild basically every time that you deploy the system. The LM API is the exact same in the PyTorch-based architecture, so you can reuse the same existing code and just upgrade your version to start deploying. If you're using a different interface, like say the Executor API, you'll have to migrate some of that over to the PyExecutor because that's more of an internal use case of the system rather than an end-to-end deployment. Typically, we'd recommend sticking with the LLM API if you're just looking to deploy a model, or using one of our higher level serving solutions like TensorRT LLM Serve or Dynamo to deploy a model end to end. It's a great question. How does TensorRT LLM 1.0 work with different backends like FlashInfer, Cutlass, and so on? So we have a lot of different kernel libraries and kernel development tools in the ecosystem. TensorRT LLM wraps kernels as Torch custom ops and enables you to bring kernels from a diverse set of sources. So we not only push kernels out into FlashInfer, sometimes when open source kernel developers put in a really awesome kernel into this library, we can easily consume it. We also leverage existing tools like Cutlass to author a lot of our own kernels. We also have internal compiler tools and techniques that let us get the state-of-the-art performance of NVIDIA GPUs using these internal compiler techniques and tools. So we have kernels from a wide variety of sources, and they're all pluggable into your model using this Torch custom op registration feature. Great question. Getting started guide. Yeah, that's a great question. It's available on our documentation. So on the TensorRT LLM documentation page, there's a quick start that shows you how to launch a server using TensorRT LLM Serve. You can also find information on our GitHub that'll include guides for a whole bunch of different models, ranging from Llama, DeepSeek, QN, a whole bunch more. It's a great question. What are best practices for managing CUDA device memory when deploying large models with TensorRT LLM? Device memory can be an interesting parameter to tweak for tuning performance of your system. Often you'll see that the weights of the model take up a certain amount of your memory, then you'll have your activations, but then a large portion of your memory is allocated to KV cache. And then you also want some amount of buffer for new requests coming in, right, with your activations. And so balancing the trade-off between these three components can really impact your production capacity, the production capacity of your system. We provide a KV cache free GPU memory fraction parameter that allows you to tune that knob and enables you to tailor the performance based on the number of concurrent requests that you'd like to serve. You can also leverage interesting techniques for compression, either for the weights of the model using lower precision formats like FP8 or FP4. And you can do the same with KV caching. We support KV cache compression with the FP8 format. to reduce the device memory footprint of your cache? It's a great question. Looks like there are a couple questions around CUDA graphs. What role does CUDA graph capture and replay play in reducing inference latency for large language models? It's a great question. So CUDA graphs is a tool that allows you to take a bunch of series of kernel launches and wrap them all together into a single kernel launch. So instead of having the overhead of multiple kernel launches from host, you can capture that all and replay it as just a single graph. The downside is that you have to pay a bit of a startup cost, right? You have to capture graphs, and particularly when you have different concurrencies that you need to support, you might need to capture multiple graphs at startup to support this. The flip side is that at inference time or at runtime, you can dramatically accelerate the performance of your end-to-end model by reducing the latency of launching kernels from host. So it's a bit of a trade-off. You trade off some startup time for better runtime performance. But CUDA graphs ultimately becomes a very essential component for runtime performance in these systems. Great question. It's a great question about conversion of ASR models. So we have some models that were supported in the old engine-based architecture. We're looking to migrate those over into PyTorch. Largely, this is going to be based on, or the 1.0 architecture. And this is largely going to be based on community feedback and engagement on our GitHub. I'd recommend raising an issue about this this model in particular, and we can take a look about prioritizing implementation in the 1.0 based architecture. In general, we found that engine building could give you good performance, but it was really hard to manage these systems and extend with new models. With the new 1.0 based architecture, we're able to deliver that same performance and even enable external user community developers to add support for their own models. So if this is something that's really interesting to you, you can raise an issue and wait for us to prioritize it, or you can take a stab at implementing it yourself and raise a PR. And we'd love to take a stab at reviewing it. Thanks for the question. Okay, I see. So there's an interesting question about what I'm assuming is the Microsoft Phi models or Phi models using some of our RTX GPUs. In general, we don't guarantee support for TensorRT LLM on RTX GPUs. We have done some demos with some of our newer generations, like the 40 series and 50 series that are based on Ada and Blackwell architectures. But in general, TensorRT LLM is designed for large-scale deployments, typically in the data center. So a lot of the work could be leveraged in the RTX family, but you're going to see most of the benefit actually on the larger data center scale GPUs. It's a good question. It's a great question here about open source community contribution, process to onboard new models. So the process to onboard new models, if there's a model that's really exciting to use specifically, please raise an issue on GitHub. We actively scan through these, respond to comments, respond to feedback, and love your help in shaping the roadmap of what's coming next. We also, of course, welcome PRs. The PyTorch-based modeling authorship makes it really easy for community members to contribute new models. So we definitely recommend, if you want to take a stab at either models or new features, to raising a PR, or use the issues feature on GitHub to help influence our roadmap. It's a great question. It's a great question about our NVL72 format of GPUs. So starting with the Blackwell generation, we designed a hardware system that provides 72 GPUs that are all interconnected and sort of act as one large GPU. This enables us to do really interesting types of deployments, large-scale deployments, including parallelization across NVL72, with experts. If you have a sparse MOE, you can splay your experts across many GPUs to drive up system efficiency. You can also disaggregate your prefill and decode phases and balance them independently using this highly interconnected system. We have a lot of guides for how to do this, both generally for disag, YDP, and how to use NVL72 on our documentation page and in our GitHub. I especially recommend taking a look at our GitHub tech vlogs that highlight how to do some of our most advanced features, including YDP and disag for NVL72. Great. One last point that I'd like to highlight is we have an upcoming conference for GTC in DC. This includes some of the industry leaders and innovators in Washington, DC, that will be exploring AI and hands-on developer training for some of these new advancements in our new technology offerings. This is a 3-day conference with lots of great sessions, as well as a keynote from our CEO. And I definitely recommend registering and checking it out. With that, thank you everyone for joining. Please engage with us on GitHub, raise issues and PRs, and I'll look forward to seeing you there. Thank you.